All right, hello everyone. Today I want to talk about standardising a linear algebra library. I'm going to be racing through this talk because I learned earlier that I have rather less time than I originally thought. If you want to talk to me about anything later today, I'm here all evening. Please do come and speak. I'm quite passionate about this. Here's what to expect. So the numbers in square brackets are slide numbers. Yes, it does go up to 271. Don't be alarmed. That is a lot of slides, but we will. I do animations per slide rather than trying to do special effects, because they tend to go wrong, really. So we're going to talk about representing linear equations, which is what is meant by linear algebra. That's what it's used for. Then we'll look at typical libraries that exist to solve linear equations, enabling promotion, stood complex, dynamic and sparse matrices, how we'll store our data, the actual classes and the API, doing the maths, and we'll walk through an example if there's time. First of all, let's look at our goals. We want to provide linear algebra vocabulary types for the standard in the library. So we want to mimic those found in textbooks, which are applicable to a wide variety of problem domains. Linear algebra is fundamental to an enormous amount of mathematics, graphics, in games, modeling worlds, image and signal processing, large simulations and things like that. I work in games. I work for Creative Assembly. I'm the principal coding manager. We have job openings. If you want to come and work for us, that'd be great. Hiring is always a problem. Games are great. We use lots of linear algebra, so I'm figuring if you're here, you might like to work in linear algebra. We want to parameterize orthogonal aspects of implementation, which means use templates. There's all sorts of customization available to you when describing linear algebra. We want to make sure nothing is left out. We want to provide defaults for the 90%, so ideally you should just be able to use it out of the box without any worry. If you're a power user, you can customize away to your heart's desire. We want to include element access, matrix, arithmetic, and fundamental operations. It needs to behave like a built-in type. And we need to support mixed precision and mixed representation expressions so that precision is never lost beyond reasonable expectation. Right. Linear Algebra 101, the branch of mathematics concerning linear equations and linear functions and their representation through matrices and vector spaces. So for our purposes, we're going to concentrate on linear equations and matrices, since we'll always be working in finite dimensional space. So a linear equation looks like this. a1x1 plus a2x2 plus an xn equals b, where an represents a coefficient and xn represents an unknown. So linear algebra, as I said, it's central to most of mathematics. We're going to look at solving sets of simultaneous equations, and then we'll look at modern presentations of geometry for defining lines, planes, and transformations. It's also used in machine learning, it's everywhere, really. Linear algebra is everywhere. And I'm going to ask, how is your maths? Has everybody got a grasp of maths? Have you used matrices before at school, that kind of thing? Anybody? Yeah, you're gently nodding. Good, good. Okay, buckle in. Put on the seatbelts. Let's go for a ride. So a vector is a tuple of scalars, like that. You can perform addition and you can perform subtraction if they have the same size, like this. You can perform scalar multiplication, b times blah, blah, blah. You can perform vector multiplication, row vector times column vector, which is called the inner product or dot product. And a matrix is a tuple of vectors. So again, you can perform addition and subtraction if they have the same dimension, scalar multiplication. Regular multiplication is a little more complicated, since the source column count must be the same as the target row count. It's not, in general, commutative. Now, there's a special kind of matrix called a square matrix, a special kind of square matrix called an identity matrix. Now, a square matrix can have a determinant, which can be complicated to calculate. Geometrically, it can be viewed as the scaling factor of the linear transformation described by the matrix. Determinants do crop up a lot. A matrix may have an inverse. It's said to have an inverse if the matrix multiplied by its inverse, or vice versa, is the identity matrix. Not all matrices have inverses. So this is rather reminiscent of the built-in types, although increment and decrement don't really have any meaning, and ordering is obviously meaningless as well. But addition, subtraction, multiplication, division, Okay, all clear? Enough theory, good. Let's look at solving simultaneous equations. We all did this at school. So we can write this as ABCD, the matrix ABCD times XY equals EF. We can see why this works. We've got, ABXY will give you AX plus BY. So we can see the important differentiation between row and column vector here. We have two column vectors there. So we can write it like this. A is our matrix. And we can rearrange it like this by multiplying by A inverse. If we multiply this by A inverse, we get the identity matrix. Nothing happens there. A inverse times EF. So let's try an example. There's our matrix A. So the inverse of the determinant times the classical adjoint is the inverse of a square matrix. Now, these are trivial to calculate for 2 by 2 matrices. So the determinant is -7. So the classical adjoint is evaluated by swapping the elements of the leading diagonal and swapping the signs of the other diagonal. So calculation is rather less trivial for bigger matrices. I'm not going to go into that. But this makes A inverse that beast. So given that value for A inverse, we have our expansion there, which gives us that, which gives us that. You can look at the video later, but honestly, that is true. I promise, okay? There are actually more efficient algorithms, row reduction, which saves you the effort of having to calculate inverses. But this, I show you this because calculating inverses is a problem with broad application, particularly in graphics. Speaking of which, let's go back to the general form of a linear equation. Now we can put this down to 2 dimensions, to the 2D plane, with a little substitution. AX plus BY equals C, just by swapping x1 for x, x2 for y, a2 for b, and b for c. So we get by equals -ax plus c, which we can, b and -a are arbitrary. It doesn't really matter what they are. What we have here is the equation for a straight line. So representing a coordinate pair as a vector, we can translate, scale, shear, reflect, and rotate this vector. So translation takes place by adding the translation to the coordinate pair, scaling by either a scalar multiplication, or by multiplying by a multiple of the identity matrix. They both achieve the same thing. So shearing is where you'll scale x and y by different amounts. So you get this kind of, shearing effect, which we achieve like this. Again, we have a single strange value up there away from the identity. Reflection, you multiply one of the axes by -1. Rotation is a bit more complicated. If you've done any geometry, this will be entirely familiar to you. If you haven't, go and look it up. It's interesting. It's exciting if you're a mathematician. But again, I promise you, this is how it works. I'm skating through this because we're short of time. We can reflect and shear at the same time. This is handy. We can stack multiple operations by multiplying matrices. So if we want to reflect and shear, we can do so like this. We can create a single matrix. And this is handy because if we want to carry out the same operation on a set of points, for example, on a very large diagram or a large mesh, if you've got 200 vertices, then you can do 201 operations, forming the stack, and then applying that to all of the vertices, rather than 400 operations, which achieves the required effect. I find this delightful. I love maths. You probably know this already, though. Right. Who here has actually written a linear algebra library? Okay. Who's written 2 linear algebra libraries? 3 linear algebra libraries? 4 linear algebra libraries? All right, I should say I've been writing games since about 40 years. I've been writing games for about 40 years. Now, I dug out my notes from about 30 years ago, and I discovered that my first linear algebra library used fixed point arithmetic on a 286 PC. Anyone use a 286 PC? You poor soul. Oh, dear. Oh. Actually, it was all right. But there was no maths coprocessor on a 286 PC, so I had to do everything in fixed point. I wanted to use SI units, obviously, and 16-bit fixed point arithmetic. So I reserved 4 bits for the fractional parts, and that gave me 6¼ centimetre resolution. So my next one exploited the floating point coprocessor. This shipped as standard with 486 processors, so that made life a lot easier. Moving to floating point, I got greater resolution. Then I made use of the SSE2 instruction set. Right now, I'm making use of the AVX instructions. I'm a game developer, so my use of linear algebra was strictly limited to matrices with between 2 and 4 rows and columns with a non-integer scalar type. That was all I did. Which means I have several optimizations available to me because of this specialization. I know the matrix size straight away. I know exactly how big all the matrices are going to be. The scalar type, at the moment, is always a 32-bit floating point type. I know about my target processor, so I can use intrinsics and SIMD instructions. I can make use of cache behavior. My library is optimized for this particular usage. Everything is fixed size and dense. There's no sparse matrices. Everything's dense. And there are many ways to optimize for other situations, such as sparse matrices of variable size. And it's like string classes. Has anyone here written a string class? Really? Wow. Gosh, I used to ask this and everyone would go, yeah, I've written a string class. It was just a thing that you did whilst you were learning C++. You'd look at the C class and you'd go, that's awful. I'm going to write my own string class. But you've obviously made peace with the string class, and okay, that's fine. There are quite a few libraries out there already which do linear algebra. I did a simple Wikipedia query, and this yielded more than I knew about. So let's take a look at some of them. The first one we all know about is BLAS. Has anyone heard of BLAS? Everyone familiar with linear algebra and BLAS? Okay, BLAS is a thing. It was first released in 1979. It's a Fortran library, and it prescribes a set of low-level routines for performing common linear algebra operations. There are C bindings, handy for us, obviously, and there are many implementations optimized for speed on particular machines. There's a C++ API called BLAS++ because we have no imagination in the C++ community, and that implements much of the functionality for your linear algebra needs. Here's an example function. You can see it takes explicit types. BLAS supports single and double float precision and single and double precision complex numbers. There's also, of course, boost.ublas. Now, I thought has anyone seen this presentation before? I've given it once or twice this year. And I've been saying that the last contribution to UBLAS was in 2009, which meant that there was no const extra and no except clauses, but I'm led to believe that's not the case. If anyone's familiar with the updated boost.ublas, I'll be interested to know. I must have been looking in the wrong place. Now, there are 3 levels to the BLAS API. Level 1 contains all the vector operations. Level 2 is the matrix vector operations. And level 3 are the matrix operations. And this gives us a good starting point for the kind of API that we want. You can see a fair amount of repetition, of course. You've got Hermitian rank, Hermitian rank update, symmetric rank update, triangular matrix multiply, symmetric matrix multiply, Hermitian matrix multiply. And it varies on matrix type and operands. And the set of operations is different for vectors from matrices. Anyone used eigen? Yes, hi. Eigen's lovely, isn't it? It's a significant advance over BLAS. First of all, it is huge. It is absolutely enormous. It is thorough. It is comprehensive. It's a big, good body of work. And it consists of a selection of class templates for matrices and vectors and operations. And it accommodates runtime as well as compile time sizes. It has a span option. It has a mechanism for dealing with non-owned data through the map class. This is important. Has anyone heard of the MD span proposal? Of course, Matoush has. Besides Matoush, has anyone heard of the MD span proposal? No, okay, look up MD span. It's proposal P0009. Quite an old proposal, worth looking at. Okay, how many member functions does string have, which are not the special functions? Any guesses? Okay, hands up for more than 10. Hands up for more than 20. Hands up for more than 30. Hands up for more than 40. The correct answer is 45. The string class has 45 member functions. Sorry? Yep. It's massive. It is massive. I counted them for this. I couldn't believe it. Anyway. And the thing I dislike about Eigen is that the API is defined through member functions. This is, we've got bad experience of rich member function classes, with string. Many of the string functions can be implemented using the algorithms header. So, it seems a bit of a duplication. We don't want to pay the cost of having member functions. Because there are so many things that are required of matrices. There's lots of things that people do. BLAS++ offers 32 member functions. The Eigen tutorial offers this sample program. I quite like this. I like the initialization. So we've got a vector v initialized via the comma operator through chevrons. So that's quite nice. It's quite easy to understand. dlib. Anyone use dlib? This is worth knowing. It's a big library of useful things, and it takes an interesting approach to matrices. One of the useful things it offers by deploying expression templates in an attempt to achieve efficiencies. I'm going to skip the explanation of expression templates. Look it up on Wikipedia. The idiom was devised by David van der Voort and Todd Veldhuizen at about the same time. It's a template metaprogramming technique that builds structures that represent a computation. So rather than returning a value, it simply returns a way of calculating the value, of evaluating what the value is, and of performing that operation. And what this means is that if you're doing things many times over through a loop or something like that, then you can effectively fuse these operations together. So you end up with less stuff going on whilst you're doing your calculations. So you can bypass the normal order of evaluation of the language this way. Look at this class. This is an example row vector class. Nothing unusual here, I hope. We've got the row vector class. We have a constructor which takes a number of elements. And we have some accessors, and we have a size of the vector, and then we actually store the things. And the operator plus, you can see what's going on here. With a plus b plus c, if you want to sum 3 row vectors, you get a temporary created for the result of the first sum, and this will require 2 loops. And delayed evaluation solves this problem and can be implemented in C++ by letting operator plus return an object of a custom type. This is kind of how they work. Say row vector sum. Do you know what? I'm really running out of time here. I'm terribly sorry. I'm actually going to skip through some of this. Yeah, that's how it all works. Look at the video, pause on each screen, and you'll understand expression templates perfectly. It'll be fine. Let's talk about std complex. There is an upsetting story to std complex. Who knows what the... actually, does anyone here use C++ for performing arithmetic? Yeah, surely. Arithmetic, this kind of thing. Yeah, it must happen. So these are standard interview questions that I use. I want to know the type and the value of A. A. What is its type, first of all? This is not a trick question. They come later. Okay, A is an integer. Okay? Whose value is 11. 7 times 5 is 35. Divide that by 3 to get 33 and 2/3. Divide that by 11. Anyway. What about this? Whoa. Confused faces. It's a long, because of that L there. There we are. Literal L. How about this one? Oh, 0. Because -3 unsigned. So -3, so the bit pattern for -3 is all sorts of ones, but it's an unsigned long. So it's a really, really huge number. So you end up with 35 divided by a massive number, which then rounds down to 0. On we go. Being explicit now about it being a long. Okay, what about this one? Yes, excellent. And this one? It's a double. That one, float, good. And we're getting to, getting to nice territory. What about this one? What's its value? -11. -3, long. It's signed, it's fine. How about that one? Ooh, the pain on your faces. It nourishes me, it feeds me to see your agony. There we are. Obviously that's the answer, isn't it? Yeah, what we're talking about is implicit conversion. So who knows their promotion and conversion rules? None of you. I don't either. No, really. I don't know them either. It's a big, long page in cppreference.com. In the standard, it's many pages. But it can be summarized easily. Small integral types can be promoted to large integral types, promoted. Arithmetic operators don't accept values that are smaller than int, okay, which is fortunate. Float can be converted, not promoted, converted to double without a change in value. Conversions may change the values with potential loss of precision. So with integral conversions, sign and width are important. Floating point conversions are a little more forgiving, although converting doubles outside the range of floats is undefined behaviour. And floating points to integral conversions merely discard the fractional part. Simply enough, rounds it down. And if it can't fit, then it's undefined behaviour. Integral to floating point conversions, return the nearest value. Look at cppreference.com. I'm not kidding, honestly. It's a good read, it's well written, but arithmetic is well defined. That's the point I'm trying to make, okay? The C++ built-in arithmetic types freely promote from float to double or from int to long, and they freely convert from integral to floating point. And I'll reinforce that, as I hear it incorrectly stated quite often. Promotion, float to double, widening representation. Conversion, integral to floating point, changing representation. And imagine not having that flexibility available to you. It would make life pretty hard. You would need to explicitly promote everything to the widest type, or up to long double, and then narrow everything back down again every time you wanted to do some arithmetic with mixed types. Not a thing you want to be doing. That's a lot of bookkeeping. That's a lot of ugly casting. I don't like casting, nor should you. Who knows what this function does? This converts, sorry? Yeah, excellent. ftol, float to long. This converts a float to long. And this used to cause me terrible trouble in game code. This is the implicitly called function when you write something like this. It's quite an expensive function, and it has to be called at runtime to convert the floating point representation of b times 3.5 to an integral type. And quite often, that integer type, that int, was arbitrarily chosen, and it would then be passed into another function which takes a float, and it would be converted back again. I would be very angry about that sort of thing. And I was delighted when auto appeared, because it bypassed all of this conversion stuff, and it meant the conversion happened where it needed to, rather than because somebody forgot about it. This is an excellent case for using auto. Now, if you've got a matrix of int, and you had a matrix of double, then you should get a matrix of double. Does that alarm or astound anyone at all? This should just work, shouldn't it? Unfortunately, it doesn't. What we need is a new type, element promotion T, which returns the resultant type of multiplying two types together. And this might seem a little trivial, but complex numbers, for reasons described shortly, complicate matters. So here's the walkthrough. We start with an is complex, which derives from false type. And then we have is complex specialized if the type is arithmetic. Otherwise, weird things are happening. It must be arithmetic. We're trying to use function pointers, matrices of function pointers. Things are very weird, and we're not interested in that just yet. So we simplify that with the Boole expression is complex V. And now we need a trait to detect if the type is a suitable matrix element. Is it arithmetic or is it complex? And again, we simplify that. And now we can move on to promotion. Okay? we have a type to resolve the element promotion type. And you can see the decal type here doing that piece of work there. So now we can simplify again with element promotion helper underscore T. You'll see there's a lot in the standard. Underscore T, underscore V. These are the kinds of things that are going on. It's just making it easier, hiding lots of this template metaprogramming. And from that, we can create an element promotion struct. And there we have it. We can specialize that for complex numbers on the right, class T2, complex number, not a complex number. We can do it this way around, complex number, not a complex number. We can do it for both. So that gives us this. We can simplify that with element promotion T. That's what we wanted, a type trait for establishing the element promotion type. Why though? Why go to all this bother? Anyone here use stud complex? Okay, there are people who use stud complex. Small audiences, you see. This is right. Quiz time again, and we'll just go through this. So the type of that, complex int times 70 times complex int 50 divided by complex int 30, complex int 17, and this is still complex int 17. It's converting all these to ints. And complex float times complex float divided by complex floats. Ooh, look, recognize that value. Right, this one. Malformed. Yes, this one. Malformed. Does this obey the principle of least astonishment? No, it does not. I saw you frown. I saw your eyebrow raise. Should the compiler be able to evaluate this? Well, yes, it should. I think this is a defect in stud complex. What should happen is that the promotion of the scalar type should be reflected in the return type, in the template parameter. I believe there are people trying to correct this. Bob Stiegel, the co-author of the linear algebra proposal, is having a stab at this. It's a bit of a big job. But back to linear algebra, we want to specialize our element promotion for stud complex because that type admits no conversion or promotion. And you might be asking yourself, is it really worth all this furniture? When am I going to need a matrix of complex numbers? Hermitian matrices. Quaternions. Quaternions can be implemented as matrices. I don't do that myself. And there's another problem. What if you want to operate on two matrices with different storage types? Let's talk about storage types. So storing your matrices is quite the topic. If you're using a fixed size matrix, then you can most likely simply keep it on the stack. Easy enough. But if you're using a sparse matrix or you don't know the size of the matrix until runtime, then you'll need to be able to allocate memory on the heap or whatever, or wherever you're keeping your free store. Alternatively, you may not actually own the values that make up the matrix. You may simply want a view on the data. You know, if you've got a stream of scalars coming in, and you know it has a particular stride, and you simply want to span on that, then you have a matrix of unowned data. And let's also not forget about cache requirements. How big are your cache lines? How do you want to store an array of matrices? Do you have access to SIMD instructions, which set? How big are the registers? How many do you have? Does your tool set expose intrinsics? Much of these are implementation details, and the purpose of standardization is to define an API, not to define an implementation. So the obvious solution is to parameterize your storage and standardize how you access the elements. So let's introduce the first class. FS Matrix Engine, fixed size matrix engine. So there's some stuff going on here. We'll go into more detail about this later. But you can see constructors, assignments, accessors, capacity, columns, rows size, more accessors that are non-const for mutable operations, and swapping columns and rows. And then we have the DR matrix engine, dynamic resizable matrix engine. Nothing too surprising here, I hope. But what we do have is reserving and resizing, because now we're looking at a container. Because we might be wanting to add data or remove data. And that's how we might implement it. Now, matrix engine negate promotion is where we have to start dealing with promoting our types. I'm going to skate through this because it's quite, again, we're running short of time. But the idea is that if we add two things together with two different engines, like a fixed size matrix and a dynamic size matrix, we need to work out what the result type is going to be. So we end up with an implementation-defined mechanism for establishing the resultant type, or the resultant engine type. And so we have using matrix engine add T is the engine type over there. And we also get this for subtract. You'll see it's just not, these haven't changed. Negate promotion, it's working in pretty much the same way all through. Multiply is a bit weird, obviously, because of you usually end up with a different sized object. Sorry about that. So here's an example of what it might look like. We'll need an allocation. We need an element type, which tells us what the element promotion is between the two matrices. Here we are, first type and second type. So this would be an example for a fixed size matrix times a dynamic matrix, where we have an element and an allocator, and we have a type and a fixed size, number of rows and columns. Let's do the maths. All of this will become clear. So here's what we want to ship: a column vector, a row vector, and a matrix. Actually, at the moment, we're considering discarding the two vector classes and just having a single vector class, which gives us a naming problem, because we already have a vector in the standard, which does something slightly different. We also have inner product. Inner product's in the standard. Modulus is in the standard. Rank is in the standard. These are all linear algebra terms that have been applied elsewhere. We're getting to that stage of name overloading, which could become problematic. Maybe we'll need another namespace for linear algebra. Now we need to define a helper trait first, enable if resizable. So if they're the same, and is resizable type. You remember those traits that you saw? That's one of them. There's spheni ahead. Is everybody familiar with spheni? You've heard about it. Good, all right. 5 years ago, this would have meant people would start playing with their phones. All right, here's a column vector. So we have the engine type, that's how it's stored, and op traits, which we'll get onto, but these are the set of operations, the set of traits, the functions that you use to perform all the operations on the matrix. So we have an engine type, we have an element type, which is stored within the engine. Now, we need some flags. Is it dense or is it sparse? Is it rectangular or is it square? Is it resizable or not? What is its size? What is its transpose type? We're thinking of a matrix transpose engine here. So in addition to having an engine to store things, there's also an engine which will return different rows and columns. When you ask for a row, it'll return the column, because that's what a transpose does. Is it a Hermitian matrix? Is it complex? Then we have boilerplate stuff. We have a default destructor and a constructor. We have a move constructor and a copy constructor, and a construct from a different kind of vector. I should point out this is the column vector. The row vector class would obviously look exactly the same. And then we have constructing with a particular number of rows, and constructing with a particular number of rows, and upper limit to the capacity of the rows. Regular stuff, assignment operator from another vector. Then we have accessors, element access. No rocket science there. The parenthesis operator, which you might know would simply, you look for vector open parenthesis 3 to return the third element of the vector. And if you want to just get all the data as a raw pointer, you can do that. So you have constant, non-const versions of that. Then we have data about the vector, how many columns, how many rows. Do you know what? This is the matrix type, I'm so sorry. And then the size, tuple, column, row capacity, transpose type and Hermitian type. And then, of course, we've got the spheni stuff. So we need to enable, we don't enable these functions for non-resizable matrices. So we can reserve, resize, and then swap rows and swap columns. But reserve and resize are only available if it's resizable, which is what this helper trait was for at the start of this section. Now let's start with negation. So matrix negation traits have an engine type, so that's the matrix negation engine, operation traits, and the result type. So here's the actual function. So the matrix negation traits struct is actually a way of exposing a function to doing the negating, this static function here. So this result type is derived from here, and the matrix in op traits is derived from here. Then we have matrix addition traits. It looks the same. It's the same stuff going on, although this time we've got two operands rather than one. Negating takes place on one operand, addition takes place with two operands. Subtraction traits would look the same. Multiplication traits, they look the same. Two operands. Multiplication is a bit more liberal about the size of what's going on, of course. So some specializations that you'd expect from multiplication traits would be multiplying a column vector by a scalar, or multiplying a row vector, a scalar by a row vector, or multiplying a matrix by a column vector. Matrix by a column vector. Or a row vector by a column vector, which is the dot product. Let's look at the dot product in greater detail. So we have our two element types, which are the row vector element type and the column vector element type. We have our engine type, which is void, because obviously a dot product just returns a scalar. There's no storage thing, it's just a literal value. Our result type is we still have to go through the matrix element promotion in case we've got a vector of floats and a vector of ints, or a vector of double. We still need to work out what the result type is going to be. But here again is our static function. And it's still from the multiplication traits, but it's a specialization of it. So we have a multiply function taking a row vector and a column vector. So we can now create default matrix operator traits. Now that we've got all these traits available to us, we can say, well, look, here's our set of multiplication, addition, subtraction, negation operations. We'll keep them in a separate class. And if you remember that second parameter on the matrix, which is the op traits, this is what you'd use by default. So we actually need arithmetic operators now. So these are free functions, so that you can multiply, non-member functions, so that you can add and multiply and do all the business here. There are simple maths to declare. Subtraction looks like this also. Negation simply just takes one parameter. There are 13 multiplication overloads at the moment with row and column vector, because you can multiply left and right combinations of matrix, row vector, and column vector. So row vector on the left, row vector on the right, column vector on the left, column vector on the right. The return types are left unspecified. That's so that you can implement things like expression templates or unusual, exotic, yet to be discovered algorithms for doing these kinds of things, for chaining results together. So here's a sample implementation, shall we say. So this is a free function, operator multiply, taking two matrix, returning auto, it's inlined. So here's our function body. So here's some, making things simpler by using op traits, because you don't want to write all this out. So op traits, and then the operand types, and then the mul traits. And then having got your mul traits type, your struct, you can then invoke the multiply function using M1 and M2. Now, how does it all work? Wow, we might get through this. I've got 4 minutes. Right, so I'm just going to declare a couple of aliases. So fixed size matrix is your regular matrix with a fixed size matrix engine of a particular type of rows and columns. Here we are, up in the templates, using the default matrix operator traits. Okay? This is handy. This is a bit of a mouthful, frankly, if you're expecting beginners to type all this out just to create a matrix of float 3, 3. That's quite a big ask, so we'll probably supply default aliases to start with. And obviously here's our dynamic matrix as well, with a type and an allocator. which is a dynamic resizable matrix, type and allocator, and default matrix operator traits. I hope that's clear. So here's an example piece of code. Fixed size matrix, double, 3, 4. That's quite clear. That's nice. I like that. That's just, look, here we are. Poof. Dynamic matrix of float. Default allocation, default stud allocator. So what would be the return type of M1? I'm going to tell you, don't worry, I'm not asking you to tell me. So what we have to do, right, we'll walk through the template metaprogramming, basically, in 2.5 minutes. Right, get in. So first of all, we have to call an operator multiply. This is what we saw earlier. So the vendor implementation might look like this, but we don't, as I say, specify an implementation. So we have 4 template parameters to resolve: ENG1, optraits 1, ENG2, and optraits 2. So going back to our example, ENG1 is the finite state matrix engine, finite size matrix engine, and optraits 1, default matrix operator traits. Now, next thing we need is the optraits, which is matrix operator traits promotion of the 2 optraits. So matrix operator traits promotion underscore T of default matrix operator traits and default matrix operator traits is that, which actually takes us back to default matrix operator traits in this case. But if there were different traits being used, there'd have to be a decision to be made. Right, op1 type, matrix ENG1 optraits 1, finite size, fixed size matrix engine. I'm sorry I keep saying finite state. I've been doing finite state automata at home for quite a while now, and I'm trying to get out of that habit. And op2 type, matrix ENG2 optraits 2 is that. So mul traits, type name optraits up here, and then the dependent name multiplication traits over op1 type, op2 type, and optraits. There. So it's default matrix operator traits over matrix multiplication traits over this matrix. It's a big old thing, isn't it? This is why we have template metaprogramming, because it's so much typing. And so there we have it. We have the default matrix operator traits, the matrix multiplication traits, and here's the left-hand matrix and the right-hand matrix. So matrix multiplication traits, what does that look like? Same process all over again. We have to figure out these 5 template parameters and then evaluate these. Fixed size matrix engine, default matrix operator traits, and the result, default matrix operator traits, which you'll recall from our earlier promotion. So engine type, matrix multiplication engine T, ENG1, ENG2, looks like this, which is matrix multiplication engine promotion engine type. So what does the matrix multiplication engine promotion class look like? We're diving down. We'll pop back up in a minute. So double, 3, 4, float, stud allocator float. So element type of the promotion is double. Alloc type, so this is a rebind. Oh, those are the days, rebind, gosh. Alloc type, so allocator double. Sorry, that just a bit of a formatting error there. Stud allocator float, stud allocator, which becomes stud allocator double. So our engine type, DR matrix engine, element type, alloc type. There we are. So we can now go back to our matrix multiplication traits, which we were trying to recall, if you remember the matrix multiplication engine type. So our op traits, default matrix operator traits. Our result type is this. So now we can actually, that completes the story. So the specialization looks like this. And you'll notice I've shrunk the font. So we have a struct matrix multiplication traits over matrix, fixed size matrix engine double, 3, 4, default matrix operator traits. Matrix dynamic resizable matrix engine floats to allocator. And then default matrix operator traits. Okay? Good, good. So using engine type equals dr matrix engine double stood allocator double. Using op traits equals default matrix operator traits. That was easy. And using result type equals matrix dr matrix engine double stood allocator double, default matrix operator traits. So here's our function. It's a static function. Here's the return type. That's just the return type. And that's the function signature. Multiply matrix constref M1 matrix constref M2 east const. Right. To recap, we suggested an implementation for the multiplication operator. And this made use of the matrix multiplication traits type, which specialized to this. All right, there's more than one way of multiplying a pair of matrices. The naive way is to iterate through the rows of the source matrix and multiply by the columns of the operand matrix. That's the naive way. Okay? You may know that your matrices contain lots of empty rows or empty columns. You might want to flag those up in some way. But that's a different algorithm. This is why we go to all this fuss, so you can plug in a different algorithm. So by writing a different set of operation traits, you can specify this. So let's take a look at multiplication. At worst, to multiply two n-square matrices requires n cubed multiplications of scalars and n squared minus n additions. That means the complexity, O(n) cubed. And although there are cache considerations to bear in mind that aren't a part of the complexity calculation, it's O(n) cubed. Let's not think about how caching interferes with big O notation. I personally think big O notation has been blown out of the water by caches, but that's a controversial opinion, which we can talk about later. The ubiquity of matrix multiplication has inspired a lot of research into superior algorithms. For example, Strassen's algorithm. Anyone know Strassen's algorithm? Okay, complexity O(n) to the power 2.807. And there's been a race to minimize this over the past 50 years. As of 2014, that complexity number has reached this. n to the power 2.372869. Who can get it down to 3.8? Money and glory and fame awaits you if you manage. There's also been research into Gaussian elimination, matrix inversion, determinant calculation, all for the same reason. It crops up a lot. It's a big thing that happens many, many, many times. So there's all manner of handy algorithms for that particular circumstance, and we cannot, therefore, require clients of our classes to use a particular algorithm. So this is why we have this second customization point, the op traits, the set of algorithms that you want to use for operations on your matrix or your vector. You may decide on an expression template implementation. You may decide that the compilation burden is too great. Expression templates do chew up compilation time. And decide on something more naive whilst you're prototyping. It's all up to you. What should the multiply operator do? We're going to have this argument. Who's familiar with the cross product from geometry? Yep, okay. So it establishes the normal of the plane described by the two vectors. And what about the Hadamard product? Anyone heard of the Hadamard product? No. This is the one that simply does element-wise multiplication on the two operands. So it's like addition, but it does multiplication instead. Has no meaning in linear algebra. And I need to be clear here, this is a linear algebra proposal. The cross product is a particular operation on two 3-element vectors. Okay? It isn't part of general linear algebra, but rather part of a particular application of linear algebra, Euclidean geometry in 3 dimensions. The Hadamard belongs in matrix analysis, not linear algebra. And there's certainly demand for an optimized multi-dimensional array library. This is why MDSpan P0009 exists. Okay, and it hopes to meet this demand. I look forward to being able to implement matrices in linear algebra using this library. So there we are, all done. We looked at linear algebra, we looked at how the problem's been solved, we looked at promotion, we looked at storage, put it all together, walked through an example. I hope you all followed the example. Let's rewind the goals. I think we've done all of these things now. So there we have it. We're still iterating on the API. We've made progress since I completed this presentation. We're still going, we're still making it bigger. This proposal is going to offer a standardized API for C++ for linear algebra, separating storage and operations and offering customizations over those parts. So Bob Stiegler and I hope to present the next version of the paper in Cologne in a few months, in July. I hope you'll all be there to cheer us on. Stay tuned. Ask me 2 questions. Please? No? All right, thank you very much.